us continue our discussion on finite automaton accepting strings. What we have discussed was containing 0, 1. Now we shall look at the complementary question, finite automaton accepting strings not containing 0, 1. So FA not containing the substring 0, 1. So we have designed an automaton which accepts set of all strings over 0, 1 containing 0, 1. Now we want the complement of that. So we have designed a machine, say M, accepting the language L of M. Now we want to design a machine M complement accepting the language L of M complement. So please note, sigma is 0, 1. Sigma star is precisely set of all strings over sigma, set of all strings over sigma, which means over 0, 1. So this will have, sigma star will have all possible strings, epsilon, length 1, then length 2, then length 3, length 4, and so on. So it's like this. Sigma star consists of all possible strings. In that, our L of M was this. Set of all strings over 0, 1 containing this. Now this part is L of M complement. Set of all strings over sigma not containing the substring 0, 1. Which means when we talk about L of M complement, what we ask for is sigma star minus L of M. So the language that we ask for is precisely sigma star minus L of M. So strings that are accepted by this machine should not be accepted by this machine, and not accepted by this machine should be accepted by this machine. That's precisely the essence. That precisely gives you the complement language. So accepted by this should not be accepted, not accepted by this should be accepted by this. So which means one can fine tune this automaton, and by flipping non-final state to final state and final state to non-final state, that will precisely ensure what is being accepted is rejected by this, and rejected by M is accepted by MC. Fine. And so simple fine tuning to this gives you the desired automaton. So let's modify this to get an automaton for this. So you have Q0, 0, Q1, Q2. There is no change in the transition except that a non-final state here becomes a final state, and final state over here becomes a non-final state. Now you see that if it's, say, look at 0, 0, 0, 0, and you see that first 0 I go here, and then I start accepting many zeros through this, and then all ones, you see that it's like this. Okay, and 1, 0 is accepted by the machine, and after 1, 0, if it reads 1, then it has, after 1, 0, if it reads a 1, it has 0, 1 in it. so it should not be accepted by the machine. So after 1 0, if it reads a 1, it is rejected because it is in a non-final state. And it may read any number of 1s, any number of 0s, and they all must be rejected, which is why we move here. So it is not containing 0 1, which means it can read any number of 1s followed by 0, and it can read any number of zeros after that. Okay, and the moment it reads a 1, then it should be rejected. Okay, so that's all. Now if you look at this machine, what is this doing? It is accepting 1 star, any number of 1s, followed by 0 star, any number of zeros. Correct? And it may accept epsilon. For example, if both start state and end state are same, then it accepts epsilon. Or it accepts just 1. You go over this. Or it accepts 1 1. Okay? And or it accepts 1 1 followed by 0, or it can accept any number of zeros, or it just accepts 0 0 0 0 0 following this. So the regular expression corresponding to this automaton is precisely this. Now one can also describe the function. One can say delta of q0 comma 1 is q0, and delta of q0 comma 0 is q1, delta of q1 comma 0 is q1, and so on. Fine. So now given a question like this, containing 0 1 or not containing 0 1, and if you are asked to design an automaton like this, it is easier to, in most of the cases, it is easier to design M rather than M complement. So design M and then flip the states, final to non-final, non-final to final, you get the desired automaton. In some cases, it may be easier to do this itself directly, then you can directly design such an automaton. Okay, so it tells you a larger message. If you can construct a finite automaton for a given language, so if DFA or NFA exist for the given language, then one can prove that its complement as a DFA or an NFA. So if M exists for the language L, then M complement exists for L complement. So that's the larger message. And there are other operations, other set theoretic operations one can do on finite automata, which we shall see next.